Hello there, Chem 111 folks. So I thought we would work on a problem together here. This is from the, what is it called? The Atomic Emission and Flame Test Lab. The last part of this, where you just have to do some calculations. It's not really based on anything that, any data that you collected in the lab. It's based on the hydrogen atom. And what we're trying to do here is figure out the initial energy level. So when an electron absorbs energy, it gets bumped up into a higher energy level and then eventually relaxes back down. And it's that relaxation process back to its eventual ground state that results in loss of energy from the atom, usually in the form of some kinds of radiation. Some of that radiation is in the visible spectrum. It turns out with the hydrogen atom, the visible light that we can see, the red or green or yellow, when we separate it into its component parts, those all end at the second energy level. So that's going to be our final energy level for our calculation. We want to know what energy level did that electron start off at as it relaxed back down. And so that's going to be our initial value. So we're going to do it just for red light. You need to still be able to do green, blue, and violet light for the lab, but I thought I'd go through the red light one with you here. And so we're given the wavelength of that red light, 652.2 nanometers. We need some other information here as well, and that is the speed of light, which is right here, the 3 times 10 to the 8th meters per second. We've also got Planck's constant, 6.63, 10 to the minus 34 joule seconds for that. And then, like I just mentioned, our final energy level that we're ending on, our principal quantum number that we're going to finish up on here, is 2. So if you can go all the way to the first energy level, that can happen as well, but that usually results in ultraviolet light, not in the visible spectrum. So that's why we're stopping here at 2. And so here's the two equations that we need for this. One, to figure out the energy for this process, we're going to use Planck's constant times the speed of light divided by the wavelength. And the other thing you got to remember here is the wavelength needs to match the unit for distance here. Our wavelength was in nanometers. We need to make sure it's in meters to match the speed of light distance unit there. So that's the first big hurdle that you got to come up with here. The other part is just getting it plugged into your calculator. So let's go ahead and do that first. So here's delta E is equal to Planck's constant. That's the 6.63. And then 10 to the negative 34th. I'll just do e to the negative 34th there. You're going to multiply that by the speed of light, which is the 3e8, or 3 times 10 to the 8th meters per second. And then we're going to divide that by our wavelength. Now, here's our wavelength, the 652.2 nanometers, but we need to have that in meters. So let me just write that. Let's do it up here. And so to convert that, we want the nanometer unit to cancel out, and we want to convert that to meters. There's a couple of ways that you can do this. The way I remember it is that 1 meter is equal to 10 to the 9th nanometers. Or there's a billion nanometers in 1 meter. And so essentially you're going to divide that by 10 to the 9th power then. That's going to give you 6.522 e negative 7 meters. Or you could also write it as 652.2 e to the negative 9 meters. You'll get the same answer with either one of those. And so again, you can plug that in down here. I'll do my 6.522 e negative 7. So again, that's how you enter it in on your calculator. Use that EE or EXP button on your calculator. If you don't, if you enter this as 6.522 times 10 to the minus 7, you can do that as well. Just make sure you put parentheses around it. Otherwise, what it's going to do is just divide by the 6.522, gets that answer, and then it multiplies it by 10 to the minus 7. We need to divide by both of these in the denominator. All right, and so that should give you, where's my answer there? 3.05 times 10 to the minus 19. And so you can go ahead and try to put that into your calculator. That answer is going to be in joules. So enter this in your calculator. See if you get the same answer that I got here. It should come up, especially with that 10 to the minus 19. If you're getting like 10 to the negative 26 power, then odds are you're forgetting to put parentheses or you're not entering that denominator incorrectly. So that's one of the big errors that students can make. So make sure you put that in there correctly. All right. Once we've got that, that is what we're going to put in here now into this second equation. Now, this equation is just based off of the hydrogen atom. This constant right here is just for a hydrogen atom. So this only works for hydrogen. And remember, our NF value that we're going to plug in right here is going to be equal to 2. So let's go ahead and plug that into that equation then. So here's our 3.05 times 10 to the minus 19, or 3.05 e negative 19 is the other way you can enter that. And then here's our constant, 2.18 10 to the minus 18. So 2.18, and again, you could put that as e negative 18 in your calculator there. 1 over NF squared. So again, NF is 2, so that's going to be 2 squared, or 4 in the denominator, minus 1 over the initial amount squared. So there's our equation. That's what we need to solve for. So here's the steps that you want to follow to solve it. It's just simple algebra, but I know if it's been a while since you've done algebra, that can be a little bit tricky too. So we're going to divide both sides by this 2.18 e negative 18. Divide by 2.18 e negative 18 there. And so when I do that, and where's my answer here? That comes out to 0.1399, 0.1399. So make sure you get that same answer there. And that's equal to 1 over, I guess I don't need that parentheses there, but I'll leave it in there. 1 over 4, that's my 1 over 2 squared. So if I do 2 squared, that's where the 4 is coming from, minus 1 over ni squared. All right, so the next thing we're going to do is move this 1/4 over to this side. All right, so another way you could write this, I'm running out of room here, you could also write this as 0.25 minus 1 over ni squared. And so to move the 0.25 over to the other side, I'm going to subtract 0.25, subtract 0.25. When you do that subtraction, that comes out to a negative 0.1101, and that's equal to the negative 1 over ni squared. So notice the two negative signs, that negative sign and that negative sign, are just going to cancel each other out. And so let me see if I've got enough room to write it over here then. So let me just flip this around. So ni squared now is equal to 0.1101. All right, again, I just lost the negative signs and I just switched what was on the left side, what was on the right side. The next thing you want to do is take the reciprocal of both sides. So let's figure out what ni squared is, not just 1 over ni squared. So all we have to do is take the reciprocal of that. So ni squared is going to be equal to 1 over 0.1101. And when you do that, you get 9.082. 9.082. All right, and now all you need to do to get ni not squared is just square root both sides. And so ni equals, and it actually comes out to 3.01, but we know that those quantum numbers have to be whole numbers. So just round this off to the nearest whole number, and that gives us a whole number of 3. So that should be our answer then. So that's our ni value. Ni equals 3 for that. And so you can do the same thing with the green light, the blue light, and the violet light. Really all you're doing, all that changes is this wavelength then. Green light's 486.1 nanometers, blue light's 434 nanometers, and violet light's 410 nanometers. Everything else stays the same. All right, so that's how you go through that. The hardest part is just getting it plugged into your calculator correctly. All right, that's the easy thing to mess up, unfortunately. So make sure you're using that EE or EXP button when you plug those in there. All right, I hope that helps. See you next time.